This is a heat capacity example problem. We have 80 grams of gold, so I'm going to write down what we know. We have 80 grams of gold, and it's at 650 Kelvin, and it's dropped into 100 grams of water, and it's at 298 Kelvin, and it's at 1 bar of pressure, and we're given some heat capacity values. The heat capacity of gold is 25.4 joules per mole Kelvin, and the heat capacity for water is equal to 33.6 joules per mole Kelvin, and we're asked for the final temperature. And so in order to work this problem, I need a little bit of space. The first thing we need to know is that energy is conserved. And that means whatever the initial heat transferred from the gold is equal and opposite inside to the change in the heat for water. And we know that the heat is equal to the number of moles times the heat capacity times the change in temperature, which is the final temperature minus the initial temperature. And so the heat for the gold has to be equal and opposite to the heat for the water. And so that one's equal to the number of moles of water times the heat capacity times the final temperature minus the initial temperature. And now I have almost everything except the number of moles I have. And so I'm going to come back over here and look at the moles of gold. I know that I have 80.8 grams of gold, and the molar mass, looking it up on the periodic table, is 197 grams. The grams cancel, and so I discover that I have 0.406 moles of gold. And, oh, I need to scribble the moles of water. I'll do that here. The moles of water is equal to the 100 grams I start with times 1 mole over 18.0 grams, and the grams cancel, and I have 5.56 moles of water. Now I can substitute everything back into my original equation, and I think then I can calculate the final temperature. So the moles of gold is 0.406 moles. The heat capacity of gold is 25.4 joules per mole Kelvin. And I'm going to multiply that by the final temperature minus the initial temperature, which is 650 Kelvin. And that's equal to the moles of water, 5.56 moles of water times the heat capacity of water, which is 33.6 joules per mole Kelvin. And that's times the final temperature minus the initial temperature, which is 298 Kelvin. And the other thing I know is that the final temperature of the gold is going to equal the final temperature of the water because they come to thermal equilibrium. And so I don't have 2 variables here, I only have 1. So I'm going to multiply these together and multiply across these 2 terms. And so what I'm going to get is 10.31 joules per Kelvin times the final temperature, and I'm going to subtract off 607.05 joules, and that's going to be equal to negative, I forgot my minus sign here, negative 187 joules per mole joules per Kelvin times the final temperature, and I'm going to add 55,671 joules because I have a negative sign out here multiplied by that negative sign. And now I want to collect my terms. I'm going to add 187 joules per Kelvin times the final temperature, and I'm going to add 6705 joules to both sides. So now I'm going to get all of the final temperature multipliers over here, and I got 197.3 joules per Kelvin times my final temperature, and that's equal to 62,376 joules. And I'm going to divide both sides by 197.3 joules per Kelvin. And I discover here that my final temperature, oh, my joules are going to cancel. I have a Kelvin in the denominator of a denominator, so it comes up top into the numerator, and the answer is 316 Kelvin.